Okay, off we go. Sorry for the late start. So, real quick before we get into the math, let me make an announcement. So I'm going to be sending out an email tomorrow after I get certain things organized. But the point is that that will be about the beginning of attendance checks, which will begin on Wednesday. So, reminder, class attendance is required and it's part of your course grade. It's small, but nevertheless significant. And we haven't been taking attendance so far because the class roster has been massively in flux up until arguably Friday. And at this point, I think it should be settled. Fingers crossed. I hope we're settled at this point. And so Wednesday, we will start taking attendance. Roughly speaking, the way it's going to work is I'm going to write a number on the board. That number will be the answer to the quiz question. And the quiz will say, what's the number on the board, right? And you'll take that quiz and enter your answer through the Canvas app on your phone. I suspect y'all probably already have that installed, but if not, you'll need to get either on your phone or on your laptop some way or another. You're going to need to be able to access Canvas just for the quiz, only for the quiz, but every day in class. So I'll have an announcement with all the details out tomorrow. That's the plan. Fingers crossed. There is a certain amount of process in getting that all set up, and I should have no problem getting it done tomorrow. But I always like to leave myself a little wiggle room. So either way, you'll be hearing from me tomorrow. Okay. All right. So back into the math. So we were talking about polar coordinates last time. Cylindrical coordinates, kind of the same thing. Pretty much the same thing. The big difference is that cylindrical coordinates is in 3 dimensions. But notice the relationships between x and y and r and theta geometrically. It's the exact same thing. These relationships are all the same as in polar coordinate. It's pretty much polar coordinates, right? The only difference is that cylindrical coordinates has an attached third coordinate called z, which is exactly the rectangular third coordinate z. So it's polar coordinates with z. That's it. That's the whole thing, right? In fact, this similarity is so strong that a lot of people will refer to this as polar coordinates in space or polar coordinates in 3 dimensions or some variation. I'll point out that cylindrical coordinates is fewer syllables, so I think it's easier just to say cylindrical, right? Anyway, but whatever. Okay. Some details, some examples, pretty straight reads. Give those a look. I do want to talk about this one though. This has a significant idea in it that I think is worth discussing. Let's talk about how to identify what surface is represented by this equation. And this is a cylindrical equation, not a rectangular equation because of the r in it, right? And there is a easy way to look at this that doesn't quite get it, right? The easy, sort of tempting but wrong way to think about it is to think, that's distance from the z-axis, and this is saying height equals distance from the z-axis, times some constant, whatever, and therefore it's tempting to say, all right, well, the higher you go, the farther you get from the z-axis. That's going to make a cone like this. Isn't that the end of the story, right? I mean, what's wrong with that analysis? And what's wrong, of course, is that this, from the very get-go, misinterpreted what r is. Thinking of r as being a distance. R is not necessarily a distance, right? R is allowed to be negative. Distances are not. How does that affect things? Things can get a little confusing here. Here's what I think is the easy way, the valid, easy way to come at a problem like this, is to make the following observation. First of all, we know this right here. If you fix a value of theta, that makes a half plane hinged on the z-axis. Any constant value of theta means we're looking kind of in some sense in some direction, horizontally in some direction, and of course vertical can do whatever it wants. So different thetas just give you sort of different half planes that, if you will, kind of rotate around the z-axis. So let's ask, how does this equation look different in different theta half planes? If I were to pick one value of theta versus a different value of theta, how's that going to change what the cross section looks like? And the answer is not at all. There's no thetas in that equation. Doesn't matter what value of theta you pick, that always looks exactly the same. Right? And for any given value of theta, it's a pretty easy argument, I think, that this equation just is going to be kind of a straight line. Right? If z is equal to r, then as r gets bigger, z gets bigger. As r gets smaller, z gets smaller, etc., etc. Right? And we know that no matter what direction we're looking in, the cross-section will always look like that. So imagine what you get then when you take this and rotate around the z-axis. If you take this and rotate around the z-axis, right, then you're going to get this cone. Sort of a two-sided, you might call it a full cone. Does that make sense to everybody? So this particular surface is not really the purpose of this example. The purpose of this example is the argument. And so two things. When there's no thetas in the equation, your surface is going to be rotationally symmetric. That's the first big takeaway. Right. Second big takeaway is when there's no thetas in your equation, you can look at any slice. Whatever you get, just rotate it around the z-axis. So it's a nice little observation, something to keep in mind in your tools for your toolbox. Okay, all right. Moving on to spherical coordinates. Spherical coordinates is also sometimes called polar coordinates in 3 dimensions. I think this is a really bad choice. I don't think it's. For one thing, we already have a coordinate system that's going by polar coordinates in 3 dimensions, right? And this isn't it. This has a little bit in common with polar coordinates, but not as much. And since only one can go by that name, I don't think this should be it. Right, so please don't think of this as being kind of like polar coordinates. It's significantly different. There are 3 spherical coordinates, rho, phi, and theta, or what we're going to call them, mostly. I'm going to go through them in order. I like to talk about theta first. Somewhat arbitrary, but again, for a given value of theta, talking about a plane, a half plane. You might say it defines a direction away from the z-axis. I like to think of it as a half plane, kind of hanging off of the z-axis, like a door on a hinge, so hinged on the z-axis. Pick your terminology. Okay, all right, so it's that angle. Theta. Okay, next. Phi. It's the lowercase Greek letter phi. How you interpret phi depends on theta. And this is, I think, a really important observation to make. It's why I like to start with theta first. I mean, again, you can do them in a different way. I think this is the natural, sort of easiest way to do it. How we're going to interpret phi depends on theta as follows. We're going to start from the vertical, the positive part of the z-axis. Phi is an angle measured as you come off of that vertical, very importantly, toward the theta half plane. Right? There's a lot of different directions that you could sort of, as you fall away from the z-axis, you could go that way or this way. We're going to make a point. Positive values of phi mean we go toward the theta axis, the theta half plane. Is that cool? And of course, now if you have a negative value of phi, well, hopefully no surprise, negative would mean you go the other direction. Negative value of phi would mean away from the theta half plane. Okay. All right. So notice then that between the two of them, right, if you've got a phi and a theta, between the two of them, that defines a direction, and that see if I can get this to cooperate. Yeah, okay. So between given a theta and given a phi, that you've got a direction coming out of the origin, and then rho, and again, this looks like a P. It's not. It's very importantly not a P. You can't use P in its place. P is a different letter of a different alphabet, right? So you got to make a point of writing this approximately as I have it done here. That's the letter rho of the Greek alphabet. And that's kind of, it's another one of these sort of linear coordinates that I'm going to loosely say tells you how far to go in that direction defined by theta and phi. How far, again, asterisk, doesn't have to be positive, so it's not a distance. If it's negative, then you go in the other direction. Is that cool? All right. Okay. There's some trig that I know y'all can handle that allows us to find conversion formulas. I like to observe that this triangle right there can be redrawn like this. You can notice that this angle phi is also this angle, sort of at the top of this triangle. And then the trig of that triangle tells you two things. It tells you, on the one hand, it tells you that R, right, the good old cylindrical and polar R, is rho sine phi. Which, by the way, we already knew that x and y were r cosine theta and r sine theta. So let's see here. So we have these two equations kind of fall in our laps almost for free, just by making this one observation that r is rho sine phi. And then you look at the other side of that triangle. That other side of the triangle is z, rho cosine phi. And now between our observation about r and our observation about z, now we have formulas for all three of the rectangular coordinates. So these are our conversion formulas, sort of spherical to rectangular conversion formulas. Make sure to know these formulas. Probably ought to memorize them, I suppose. It's a little faster to have them memorized than to rederive them every time. That said, for your consideration, I've never memorized these formulas myself. I trust my ability to do trig more than I trust my ability to remember stuff. I'm fairly sure that for myself, everybody's different, I would misremember these in some way or another, and then my entire calculation would crash and burn. I just don't trust myself, right? So anytime I need these formulas, I'm thinking this picture right here. Does that make sense? All right. Okie dokie. So I'm going to skip down to this example here. We're going to get a little practice thinking about spherical coordinates. This is very challenging geometrically. There's a lot of sort of like just trying to visualize and see what does this look like. Give yourself the time as needed to think this through. Right? I'm going to go through this kind of quickly in some sense. Right? But take the time to fill in the blanks and write down the details of the stuff that I'm gonna point you in the right directions here and make sure you get all these details. Okay, so first of all, we're going to start off with this point. This point right here. You'll notice I'm giving these x, y, and z coordinates of that point. You'll notice that some triangles show up and trig and all that, and you can persuade yourself, I think, without too much trouble of what those angles are. Make sure you can do that. Right? That's just trig. And with all of those particulars, we're now going to ask, what are the spherical coordinates of that point? And it turns out there's more than one way to do it. Remember, we talked about polar coordinates. With polar coordinates, there's infinitely many ways to do it, because you can always add 2 pi, right? You can add 2 pi as many times as you want. Ignoring that, because it's sort of obvious, right? Ignoring all the 2 pi's that you can add for free. There's 2 ways to represent a point in polar coordinates. in some sense, you can have exactly the right angle, or you can have exactly the wrong angle and then a negative value of r. Right? Does everybody remember that? Okay. Same story here, except now there's two angles. And for each of those two angles, there's going to be sort of a right way to do it and a, if you will, wrong way to do it. And so two angles, each of which gives you two possibilities. There's actually four different ways to represent a point in spherical coordinates. Okay, so let's talk them through. The first way to do it, we're going to make some what I'm going to call the obvious choices. So theta equals pi over 3 gives us a half plane kind of like this. And then let's see how far off of that vertical do I need to rotate down to go in the correct direction. Well, I've already computed that angle, pi over 4. So theta equals pi over 3, phi equals pi over 4 will get us going in the right direction. And then I think you can do the calculation to see what that rho is. Let's see, that's 2 square root of 2. Is that cool? Okay, so that's our first of 4 different ways to represent that point in spherical coordinates. All right. Let's think about the second one. What you might call the second one. Same point. Let's observe that from the vertical, instead of going in the positive phi direction, keep in mind the positive phi direction is toward the theta half plane. Instead of going in that direction, what if I went the other? What if I went backwards? Right? And then I kept going backwards until I got to where I was going exactly the wrong direction. If you're going exactly the wrong direction, well, then you can just choose a negative value of rho, and it gets you right to the exact same point. Does that make sense to everybody? So let's talk about what this value of phi is here. What is this value of phi? There's a couple of ways to think about it. You can think about what the magnitude of that angle is just by kind of looking at this is pi over 4, so this must be 3 pi over 4. Right? Because they clearly add up to a pi because they're a half turn. But careful, don't forget, this is in the negative phi direction, so this would be negative 3 pi over 4. So that's one way to think about it. Arguably an easier way to think about it is that we already knew that this was pi over 4, and just subtract pi. Well, again, negative 3 pi over 4. You get the same answer. What do you think? Did you buy it? Yeah.
Or pi over 4 plus 5.
Yeah, also, yeah, you could plus instead, absolutely. So 5 pi over 4. That'd be a perfectly valid. So that's what I'm going to say it's equivalent, because remember you can always add or subtract 2 pi. And so what you did is you added 2 pi to the angle that I had described. So perfectly valid, absolutely. Okay, let's think about the other 2 ways to do it. Now keep in mind, these were 2 of 4 candidate ways to do it. The other way to do it is to use the other theta option, which is where I don't just do this, but I keep going all the way around until I'm going exactly the wrong direction. All right, imagine this value of theta, 4 pi over 3. Right, that's facing exactly away from where my point is. Yes?
Why would you want to use the other method?
Oh, it's not that we necessarily will have right now any compelling reason that we want to. This is just a we can, and let's make sure we know how to do it, just in case. Just want to be prepared for anything. Yeah. So, okay, so 4 pi over 3 for theta. Now, which way should phi go? Well, we've already talked about how, this is kind of the obvious way to do it. And here's the dangerous part. We have previously talked about this angle we have previously talked about sort of leaning toward the point in question, and we described this as being phi equals pi over 4. It's not pi over 4 anymore. Remember, the positive direction for phi goes toward the theta half plane, so this is now negative pi over 4. Phi is negative pi over 4 here. Does that make sense to everybody? Gotta be careful with these little details. Right? And then again, of course, the other option would be to go the other way, and I think kind of the easiest way to think about that is add pi. That gets you going this direction. Let's see, we had been at negative pi over 4. You add pi, that gives you positive 3 pi over 4. That gets you going exactly the wrong direction. And then a negative rho will get you to where you want to be. Everybody see how this game is played? So this is very geometrically challenging, tricky, right? I encourage you to think all of this through on your own, draw your own pictures, think through, write down the angles, plug in to our conversion formulas. Right? The values that you get, plug them into here. Make sure you get the correct X, Y, and Z as you should. Okay. All right. Okay. Here's a related observation. This is just kind of cute, so we're not going to spend a lot of time on this. But if you set up planet Earth with the center at the origin, with the North Pole on the positive part of the Z-axis, and with the prime meridian in the exact direction of the positive part of the x-axis. It's arbitrary, but pretty standard. If you set up planet Earth like this, notice that east longitude, right, is exactly theta. It's exactly the spherical coordinate theta. How about that? Notice further, north latitude. Now that's not phi, right? Phi goes the other way. Phi comes down from the North Pole, not up from the equator. But even though phi isn't exactly north latitude, it's pretty easy to notice a relationship between phi and north latitude, because they always add up to pi over 2. Right? You can see how the blue and the orange are sort of complementary parts of a right angle here. And so they add up to pi over 2, and thus this. Is that cool? Everybody happy? And then now, one last little observation. If you're looking at a point on the surface of the Earth, and keeping in mind that the center of the Earth is the origin, notice that rho is always the radius of the Earth. Which, I mean, let's go ahead and use a sphere to approximate the surface of the Earth. Not exact, close enough, whatever. At the level of the thousands of miles that we're talking about, the little, Mount Everest is teeny tiny, right? So let's call it a sphere. So notice what this tells us then, that if you have the spherical coordinate, if you have the map coordinates, longitude and latitude, if you know where points are on the map, you can plug into here and you can infer the spherical coordinates of that resulting point. Let me show you why that's useful. If you ask this very reasonable question, given 2 points on the surface of the Earth, I like to think of them as being New York and Moscow. I know that seems about approximately geometrically correct. How would you compute the distance along the surface? Right now, to emphasize, we're not talking about the straight line distance. We're not going to tunnel underneath the surface of the Earth, right? First of all, we'd melt. That's all magma down in there, right? So can't do that. I want to go along the surface. Tempting to pull out a map and draw a little triangle and do a little Pythagorean calculation. You can't. Maps distort distance. Some of them really severely. Right? So that's nonsense. Absolute garbage. How are we going to compute this distance? And it's a lovely little argument. The big idea is if you know the map coordinates of these points, use what we just did, write down the spherical coordinates. Use what we did a page back to write down the rectangular coordinates. Now you have the rectangular coordinates of these 2 points, aka you can think of them by their position vectors. It's really easy to compute the dot product once you have the rectangular coordinates. Dot products are always magnitude times the cosine of the angle. You know the radius of the Earth. You know that dot product, easy arithmetic. Take the arc cosine, solve for alpha. That gives you this angle here. And then multiplying by the radius of the Earth will give you the distance in question. Yeah?
Are we able to do dot products with spherical coordinates?
That's a great question. Not really. No, spherical coordinates are not convenient for that kind of thing. Yeah, so, there's probably some formula somewhere, but I've never seen it, and it's not anything you need to worry about. Right. Yep.
Would you be given the angle in between R2 and R1?
Would I be given what now?
The angle for the cosine? Or would you have to...
Well, in general, computing an arc cosine is not computationally reasonable, right? So I would, if this showed up on a test, let me rephrase that. If it showed up on a test again, because it has showed up on midterms in the past, I forget how many times, but it's in there. You'll find them, I'm sure. I might ask for the cosine of the angle, or I might make the points particularly convenient points where finding the angle would be arc cosine of half or something easy like that. Yeah. Right. Yes.
In general, should we convert back to rectangular coordinates before we do any operations on it?
Yeah, if you want to do vector addition, spherical coordinates not particularly helpful. Yeah, absolutely. So it's another one of these, right tool for the right job, kind of thing. So spherical coordinates has its moments that are extremely useful. And we're going to see there are some integration techniques that require using spherical coordinates. Those integration techniques are indispensable when you're doing certain computations in quantum mechanics and E&M and stuff like that. Absolutely. But for stuff like adding vectors, they're terrible. Yeah. Okay. All right, so I think that's a cute little calculation. It looks like a very, very difficult problem until you realize the little trick there. Okay. Easy little bit of algebra here. If you have a rectangular equation and you want to figure out what is the corresponding spherical equation, again, you just plug in the conversion formulas. It's no big deal. You can see part of that process where I literally just plugged in for this x. I plugged in the formula that we have for x. There it is. Right? So all you got to do is plug in. You will notice, though, that before I did that, I went ahead and expanded this square. I expanded that out. And the reason I did that before I plugged in is because I saw that would allow me to use that awesome little shortcut right there. Very convenient. It did a lot of my trigs for me. Right? By noticing that was something that I could sort of aim for, right, and then let that formula do a lot of my work for me. So heads up for opportunities like that. Okay, how we doing? Everybody all right? Okay. Unfortunately, there is not perfect consistency between all people who use spherical coordinates as to exactly what we should call the spherical coordinates. It's very frustrating that physics classes will use a different convention than math classes. It's kind of played out for historical reasons. And there's sympathetic explanations, but anyway, the punchline is heads up. right? And this is on you. I can't change the way of the world, right? The way of the world is there are different conventions used in different contexts. So keep your eyes open. Don't just assume when you see work in spherical coordinates that they're using the convention that you might prefer. Right? So there are some policies that I'm going to talk about here in a minute, but first I want to point to what the other most common convention is. This is what physicists use very commonly, and you'll notice that what we call rho, they call r, which is particularly confusing because we use r to represent something else. So, heads up on that. The other really frustrating, arguably more frustrating, pros and cons, what we call phi, they call theta, and what we call theta, they call phi. Oh my gosh, right? So, now again, it's not my fault, right? But both conventions are in use in different contexts, and what you're gonna see will depend on the personal preferences of whoever it is setting the standards for that context, right? So in physics classes, it'll be mostly this. Our math book does the other that we've been working with so far, right? And so you just have to always let context be your guide, right? Be on the lookout. So, okay, a couple things to say. I've already kind of said this one. Don't just pick one convention and decide I'm going to be a rho phi theta kind of person and I'm always doing rho phi theta. You can't. In these other contexts, that would be unacceptable. Right? You have to be flexible. You have to be able to work with either. And by the way, as someone who did a math physics double major in college, I've had to become comfortable with both. In fact, in the same semester, it's like, my math class did one, and then I go over to my physics class, and everything's backwards, right? And you just got to be able to roll with that, right? So it's annoying, but got to do it. Thankfully, our textbook seems to use a single convention. That's kind of convenient, right? For any corresponding book exercises, interpret according to that standard Kali convention. As a general point, very often, either an exercise you're doing for the homework or an exam question on the test you're taking will establish a convention. You have to stick with that. You can't say, I don't like this setup. I'm gonna switch from the physics convention to the Kali convention. I like to do everything with the Kali convention. Nope. You got to use the context as it's set up in, be it the exercise or whatever exam question. You've got to do it with whatever convention has been established. Does that make sense? I hope that seems, yeah.
If I get an exam question, am I allowed to switch the convention to something that's comfortable with me, and then in the final answer switch it back?
No, because we're looking at the whole thing. And so if you do that, first of all, that would confuse the heck out of everybody, right? But we have to grade based on what's written, and so we would basically have to interpret everything. All of your supporting calculations would all be interpreted as wrong. Yeah. So I'm sorry, but you can't do it. Yeah. Yes.
Can we assume that for all of your exams will be using theta or theta phi?
I wish we could say so, but unfortunately, no. Yeah. Right. Now, for whatever it's worth, on my past exams, up until a couple of years ago, I think that happened to have been the case up until a couple of years ago. As of a couple of years ago, the department decided that we wanted to start getting students comfortable with being able to do it either way. And so I don't remember if I have any R theta phi questions on my recent old exams, but I think I might. I just don't remember for sure. Yeah. Now, here's one thing for you to consider. With rectangular coordinates, right? This is usually X and this is usually Y, and that's pretty standard, and I think pretty much everybody has seen two-dimensional rectangular coordinates done like this, right? And yet, if you were in some other context, like an econ class, and I think they do like, I can never remember if they do PQ like this or if it's the other way. Not that it really matters, right? But in an econ class, they'll do all sorts of stuff where they'll have P and Q instead of X and Y. And y'all are accustomed to this kind of thing. There are, engineering and physics situations where maybe instead of Y as a function of X, maybe it's V as a function of T, or T as a function of A, or whatever, right? There's a million different variations, and y'all have adapted to all of that. So really, this is not that different, right? So I hope you'll view this as being, a kind of an eye roll, sort of a micro annoyance, and not actually a real problem. But anyway, do be careful. Here's the last thing I'm going to say about it, and that is, in those circumstances where there is no established convention, you are welcome to choose whichever convention you want to work with. It's up to you. The only asterisk is you have to make your choice unambiguously clear. Right? So you can't sort of just write down whatever you want and then decide after the fact what it means, right? So you have to, on the test paper or on your homework, establish unambiguously what your convention is. Now, there's a couple ways you can do this. You could just write down those conversion formulas appropriate to whatever choice of notation you're choosing to use. That'd be one way to do it. It's a little heavy-handed, but you could. Another thing you can do is you can write like so and list what you're calling the coordinates, and just make sure that whatever you list first is the radial coordinate. Whatever you list second is the vertical angle, which by the Kali convention is phi, by the physics convention is theta. Right? So radial coordinate first, vertical angle second, and then horizontal angle third. Right? So if you stick to that, this is very standard. Right? So radial, vertical, horizontal. So for example, you can just write down spherical rho phi theta. All good. Everybody knows what you mean. Perfectly unambiguous. Or if you want to do it again, like the physics way, then you would just say spherical r theta phi. Everybody knows what you mean. Does that make sense? All right. Okay. All right. Standard basis vectors. Y'all know these, right? I, J, K, ones and zeros. They're the vectors pointing in the direction of the axes. Reminder, I like to call them E1, E2, E3. I think that's got some nice advantages. These are the rectangular standard basis vectors. You can ask instead, for example, what are the polar standard basis vectors? And the idea here is that for any given point, wherever you might happen to be, we can ask which direction is, for example, r increasing. So from that purple point, if I wanted to hold theta constant and increase only r, well, that's that direction, and there's a formula for it. So this is called a polar standard basis vector. And then likewise, if I were going to hold r constant and increase only theta, thus kind of going around like so, notice that at the start anyway, I would be going in that direction. And there's a formula for it. So between the two of them, these are called the polar standard basis vectors. They are useful in a lot of ways. You'll be using these in physics classes. at various different points. I don't know about engineering classes. I would think probably, but I don't know. By the way, this is I just wrote down these formulas here. I think it is a good exercise. You'll notice I have it labeled as optional, good background, but it's not expected to be tested. You don't have to derive these formulas, but I think it's a really nice exercise. Give it a try, right? I think you'll find that the first one in green here is pretty reasonable to write down, and then I'll observe that the blue vector is always a 90 degrees counterclockwise rotation of the green vector. And y'all know how to write down rotation matrices. That'll help you find this blue E theta vector. Okay. All right, likewise in spherical coordinates. And again, you got to kind of think through the geometry for any given circumstance. If you're at a point like this, and ask, well, which direction do I go if rho increases? Well, it'd be like that. In which direction would I go if theta increased? Well, as theta increases, I'm going around sort of the z-axis, which would have me going that way, etc. And those you can write down formulas for. And again, good little geometry exercises, and I encourage you to give them a good old try. If you get stuck, come talk to me in office hours. Happy to help. Right? But, yeah, good things to know. Okay. All right. Bad news. As you can tell from the picture here, they're not constants. That's annoying. Right? Think about our regular rectangular standard basis vectors. Ones and zeros, they're constant. They're always the same. No matter where you are, E3 is always straight up, 0, 0, 1, no matter where you are. Not so with, let's say, well, easier to draw the picture up here for the polar standard basis vectors. For the polar standard basis vectors, for a point here, for example, notice ER is about like that, and E theta is about like that. So both are different depending on where you are. Not constants. Okay. The one little bit of good news, and this is really nice, is they all happen to be orthogonal. So the polar standard basis vectors are orthogonal to each other. The cylindrical standard basis vectors are orthogonal to each other. And the spherical, likewise, orthogonal to each other. So that's really useful. Okay. All righty, moving along. So we're done with chapter 1. Moving on to chapter 2. The first couple of bits here, again, it's a lot of details. I think it's pretty readable. You just have to, think through the details, read for specifics, and I think that's all pretty readable. I'm going to go down to sort of, in some sense, what this is building up to, and that is the idea of invertibility. So here I have a couple of functions. Here's a domain. Here's a target. That's just terminology. The domain is language that says, where are the inputs going to come from that I'm going to plug into a function? Target says, where are the outputs always going to land in that come out of the function? So I like to think of the domain as kind of the input space and the target as being sort of the output space. It's kind of intuitive. So here's a function that sends that point to there and that point also to there and that point to there. This function is not invertible. If I were to look at this function here on the left and say, hey, what would happen if you turn those around backwards? What's the function that sends everything back where it came from? Well, where did that point come from? It came from two different points. I can't pick what should be F inverse of that purple point there. I don't know. I've got two candidates. I can't just choose arbitrarily. Right? And then also a problem. Where did that come from? How do I decide where to send that back to where it came from? It didn't come from anywhere. I have no candidates. Right? So that's not an invertible function. Invertible would look like this, where you notice each one of these arrows, if I just turn it around, I've got a perfectly good function going the opposite direction. For every one of these points, I have exactly one corresponding output, new output of the inverse there in blue. So perfectly invertible. Does that make sense to everybody? Okay, now this is the kind of thing that a lot of high schools are really, really sloppy about. And let's talk about the square root, for example, square root function. A lot of people would say square root, well, just invert the square function. I mean, come on, what's the big deal? But here's the thing. This function, the squaring function, whatever input you give me, I'm going to square it. By the way, I can do this for any real number. Why be fussy about the numbers I'm putting into the squaring function? I can square anything you give me. Whatever comes out, it's always going to be a real number. Do we really need to be more fussy about this than that? A lot of people would say no. There's a perfectly good function. And it is not invertible. You cannot talk about the inverse of that function. It doesn't make any sense. What is f inverse of 25? I don't know. It could be 5. It could be negative 5. It could be either one. I don't know. How am I supposed to decide? I don't know. It's not well defined. Everybody see the problem there? Okay. So to make this an invertible function, what we have to do is we have to restrict the domain and the target. I'm going to allow only, strictly only, non-negative numbers to go in there now. And I'm going to allow only, strictly only, non-negative numbers to come out. And now if I say, no, same function, by the seeming, it looks like the same function, same formula anyway, seems like it's the same function, but with a different domain and a different target, this is now invertible. So it doesn't make any sense to call f and g here the same function if one's invertible and one isn't. Right? That doesn't make any sense at all. So this is why we have to be fussy. It's not really that fussy if you really think about it, but it feels fussy at the start. We have to be fussy about what exactly do I mean by the domain and what exactly do I mean by the target, because that's going to matter when we try to invert the function. And this is a really nice example. So making these restrictions like I have here, this function g is invertible, no problem. And when you invert it, for every number that came out of the squaring function, there is exactly one corresponding number that went in to the squaring function. And this is the inverse function. That's how we define the square root function. Does that make sense to everybody? Everybody happy? Okay. All right. So likewise, by the way, with sines and cosines, this is the kind of thing that, again, a lot of high schools. By the way, I don't even know if I would criticize high schools for this. Most of the students at most high schools aren't going to be in a class where it starts to really matter and stuff like this. And we have to be careful, right? But anyway, many of you might not have seen what I like to call the invertible sine function. This is not regular old sine theta, where you can put any number in and whatever. I don't feel the need to get fussy about what comes out. Real in, real out, fine. Right? In a lot of high school settings, it's perfectly good enough. In this setting, again, fussy. Only these angles allowed to go in, and allowing only these numbers to come out. This function, which I'm going to represent by way of its, what the graph looks like, not only is it true that for every green there's exactly one blue, but likewise vice versa, for every blue there is exactly one green. So this is an invertible function. Again, I call it the invertible sine function, and arcsine is the inverse of that function. By the way, make sure you know about the unit circle. I think this is really worth knowing. You can think of angles as sort of on the unit circle. Sine, of course, is the y coordinate, and view this as being sine or arc sine depending on which way you're going. But the reason we choose those green values and those blue values is because this part of the circle is in perfect one-to-one correspondence with this part of the y-axis. I think this is ultimately really a more natural way to think about sine and arc sine, because it's kind of a constant sort of picture. Anyway, I think it's better. Okay, all right. Good place to draw the line. We'll stop here. See y'all later. Have a good Monday. See you on Wednesday. And don't forget about the attendance stuff.
I have a really quick question.